So here we have the standard cubic function. Fx is equals to ax cubed plus bx squared plus cx plus d. And again, we are going to look at the value of a in front of the x cubed to determine the shape. So when a is positive or bigger than 0, we have three types of cubic functions that can be formed. But in general, they have the same shape. The first type of function that can be formed starts on the left, it moves up, reaches a stationary point, moves down, reaches a second stationary point, and then goes up again. But can you see from left to right, I first go up. That is when a is positive. The second type one only has one stationary point instead of two stationary points, but it follows the same trend. So starting from the left, the graph goes up and it continues to go up after the stationary point. The third type of one you can have is one with no stationary points. But as with the other two, starting from the left, it immediately goes up and it continues to go up. So all 3D shapes from the left start by going up first, and that is when a is positive. So when the a value in front of the x cubed is negative or smaller than 0, then it's the opposite. The graph starts from the left, it goes down first. So for all three variations, it will go down first. The first type of graph will have two stationary points. The second one only has one stationary point. And the last variation has no stationary points. But it's important, when a is negative, the graph from the left goes down first for all three variations. Now that we understand the impact of the a in front of the x cubed on the graph, we can speak about where the cubic function is increasing and decreasing. And when we speak about increasing and decreasing, we are going to work with the gradient. So in this example, we have fx is equals to x cubed minus 2x squared minus 15x. And we want to determine where it's increasing and decreasing. So what I want to determine first is if there is any stationary points and at which values of x those stationary points are. So I take the first derivative of fx. So x cubed will become 3x squared. Negative 2x squared would be negative 4x. And negative 15x would be negative 15. Now remember, this is an equation for the gradient. But it's also, if we place the gradient equal to 0, we'll find the position of the stationary points. So what I can do is I can factorize 3x squared minus 4x minus 15. And when I factorize it, I get 3x plus 5 and x minus 3 in my second bracket. Now I solve x. So x is equals to negative 5 over 3. And x is equal to 3. In this question, we're not looking for the x-intercepts or y-intercepts. We simply want to determine where the graph is increasing and where it's decreasing. Now the value in front of x cubed is 1, which is a positive value. Therefore, we know what the shape would be. And we have determined that there are two stationary points. The one stationary point on the x-axis is where x is negative 5 over 3. And the other stationary point is where x is equal to 3. And remember, the shape comes from a is equal to 1. So starting from the left, I move up first to the stationary point, down, and then up again after the second stationary point. Remember, we are not concerned about the x-intercepts. We simply want to see where it's increasing and decreasing. And I can see that it is increasing on the left of -5/3, and it's also increasing after 3. So if I move from left to right, the gradient would be positive before -5/3 and positive after 3. So the function is increasing where x is smaller than -5/3 and where x is bigger than 3. Therefore, the function would be decreasing between those two values. So if I move from the first stationary point to the second stationary point, I can see I'm moving downwards. So it's a decreasing gradient, or the gradient would be negative. And then I would say the graph is decreasing for x between 3 and -5/3. This example, we are going to determine what is happening at specific values of x. So whether it is increasing at or decreasing at x equals to -2, x equal to 0, x equals to -1, x equals to 3, and x equals to 2. Now what you need to remember is increasing and decreasing speaks about the gradient, and the gradient of a function is determined by its derivative. So I need to differentiate the function, then I'll have a formula for the gradient. If the gradient's value is bigger than 0, it will be increasing, and if the gradient is smaller than 0 or negative, then it will be decreasing. So for this example, we will be looking at fx equals to 2x cubed minus 3x squared minus 12x. The first thing that we need to determine is an equation for the gradient. So if I differentiate 2x cubed, I have 6x squared minus 6x minus 12. Now I was given specific values of x of -2, 0, -1, 3, and 2. And all that we need to do is substitute those values of x into the gradient formula to determine the actual gradient at that point. So where x is -2, the gradient where x is -2 is 24. I simply substituted -2 into the formula for the gradient. But that value is bigger than 0, meaning the function would be increasing where x is equal to -2, or it will have a positive gradient where x is equal to -2. Our next value was where x is 0. So in the gradient formula, I substitute x of 0 and I get -12, which is smaller than 0. Therefore, the function is decreasing or has a negative gradient at x equal to 0. So this value is not the gradient value, this is the position of x, and at that position the gradient is -12, which shows me that the graph is going downwards. Our next value for x that we substitute in is -1. And when I substitute -1 into the formula for gradient, I get 0. And where the gradient is 0, that is called a stationary point. So there would be a stationary point at x equals to -1. Our fourth value for x that we substitute into the gradient formula was 3. So where x is equal to 3, the gradient is 24. And therefore, it is positive, and the function is increasing at x equals to 3. Our last position of x that we substitute into the gradient formula is 2, which is also equal to 0. So therefore we know that that's a stationary point at x equals to 2. In our final example, we're going to speak about concavity. So we have concave up and concave down. Now in one of the previous lessons we have touched on the shape of concavity, and now we are going to determine at which positions of x is it concave up and concave down. So if I take the second derivative and it's bigger than 0 or positive, then it will be concave up. And if I take the second derivative and it's smaller than 0 or negative, then it will be on the part of the graph that is concave down. Now remember, concave up is if I follow from left to right and I were to just complete that shape, it will move upwards. And concave down is if I follow from left to right and I follow the graph, it will go downwards. So let us look at the example. Here we have fx is equals to negative x cubed minus 6x squared plus x. And I want to know whether it is concave up or concave down at these 4 different values of x. So first we need to find the first derivative. So I apply the rules of differentiation on each and every term separately to find negative 3x squared, negative 12x plus 1. Then I need to find the second derivative. And all that it is to apply the rule of differentiation on the first derivative again. So negative 3x squared would become multiply in front of the 2, so it's negative 6, and then subtract 1 from the exponent. And for 12x, the exponent is 1, so it's negative 12 times 1 is negative 12, and then subtract 1 from the exponent. And 1 doesn't have any variables, so I don't apply differentiation to it. Therefore, the equation of the second derivative is negative 6x minus 12. And this we use to find the point of inflection and also to determine whether or not the graph is concave up or concave down. So our first value for x is negative 3. So I substitute negative 3 into the second derivative. And if I place negative 3 in here, the value would be 6. The 6 is bigger than 0, therefore at x equal to negative 3, the graph would be concave up. Our next value that we substitute is x equal to negative 1, and we place it into the second derivative, so I replace that x with negative 1. And the value that I find is negative 6, which is smaller than 0, so it's on a position on the function where the graph is concave down. Our third value that we substitute in is 0. And when I substitute 0 in, I have negative 12. So negative 12 is smaller than 0, which means where x is equal to 0, the graph is concave down. And lastly, we have a negative 2. So when I substitute negative 2 into the second derivative, I get 0. So it's neither bigger than 0 nor smaller than 0. So there's no concavity. And that is the point of inflection. So that is the point at which it changes from concave up to concave down.